We'll start our lecture on statistical inference today. And so far we have discussed, given a probability distribution for a random variable, how can we answer questions such as, what is the probability of x, the random variable, falling between a and b? And given the probability of 80%, how do we find a and b, the two values? Also, we discuss how do we calculate expectation. And more importantly, we discuss the proper interpretation of these quantities in terms of the random variable as an underlying physical process. We also learn to use the random number generation coupled with a given probability distribution to simulate an uncertain process or multiple processes to simulate a complex business situation for which a solution is otherwise not available. But you might have been already curious about how we come up with such a probability distribution that can accurately describe the underlying random variable. This is the issue that the statistical inference is trying to address. Specifically, statistical inference is to find out ways to draw conclusion on or find a distribution for a random variable from the observation of the random variable in questions. So we will cover two types of statistical inference in this course. The first one is called hypothesis testing. It's about how to determine whether or not a random variable indeed follows the given probability distribution. And the second type of statistical inference we will cover is called estimation, which is to find the distribution, such as the shape of the density function, the actual function form, to describe a random variable given observations for the random variable. We'll first look at hypothesis testing. We'll use an example in quality control, which is about how to monitor a cereal box filling process. So if the process is in control, the weight of each cereal box follows a normal distribution with the mean as 368 grams and a standard deviation of 15 grams. So the quality policy requires us to shut down the production line if the process is drifting away from this specified normal distribution. So obviously we need to look at three things. Number one is we need to check whether or not the distribution indeed follows normal distribution. The second thing we need to look at is whether the mean, which is 368 grams, stay as specified. Similarly, we need to look at the standard deviation to see whether or not is indeed equal to 15. So how can we go about doing such test? Let's look at first the way of testing by a graphic comparison. For example, we can collect a day worth of cereal boxes. Let's say it's 10,000 boxes produced per day, and we can weigh each one of them, and we can create a histogram for X, which is weight per box. And once we create such a histogram with 10,000 boxes, we could compare it to the specified density function. In this case, the specified density function is a normal distribution with the mean of 368, and then the standard deviation is 308. The standard deviation is 15. So this is the histogram we created based on our 1 day's work, and the red curve is the specified density function. And notice the chart could be measured in a raw scale in X value, or in a standardized normal scale, the Z value. So if the picture looks like the one we are looking at right now, then there's no reason to believe the process is off. And one thing to notice is, if we measure a large quantity of boxes, and based on which we create histogram, we can create a histogram with really small interval, and therefore the histogram would almost morph into a smooth curve. And the reason that we said earlier, there's no reason to believe the process is off, is because the histogram traces very closely to the specified normal distribution density function in this case. Now let's look at the second figure. Now again, this is the smooth histograms if we have enough boxes measured. But in this case, in the figure 2, we notice the observation is no longer a normal curve because it's skewed to the right. So this will make us to conclude that the observation is no longer a normal distribution. Figure 3 shows the observation, again based on the histogram, looks normal. However, its mean is no longer in the center. So that's another situation where the process could be off. And lastly, the figure 4 shows us another situation where the process could be off. So again, this pencil curve is the actual observation, and we can see even though it looks normal and is still centered at the right mean, however the standard deviation is become wider than what is specified. So figure 2 and 4 shows 3 different ways of deviating from the specified normal distribution. But of course, in reality, the deviation could caused by combination of all these 3 situations. So these type of graphic comparisons are really straightforward and intuitive. However, they are not precise. For example, visualization is really subjective. You might conclude these 2 curves follow each other fairly closely, but someone else might disagree. So this is the first problem of tests based on visualization. Another problem of this kind of testing procedure is it requires a huge amount of boxes being measured. So it is likely that you will find out at the end of the day that the process is off from the very morning. So you would end up with a huge amount of waste. So in this lecture, we're going to cover a statistical and inexpensive way of testing whether mean in D equal to 368. So that implies we need to make assumption that it is follow normal distribution, and we also need to make assumption that we know the standard deviation is equal to 15. So to to test normal or to test normality using a statistical way is covered in chapter 6.3 in the textbook, and to test in a statistical way that standard deviation is equal to 15 is actually covered in chapter 12.7. So we are not going to spend time on these two type of tests. So to test the mu equal to 368 in a statistical way requires us to use hypothesis testing, which we'll turn to next. Hypothesis testing. We will use illustrative examples here to demonstrate some basic notions and terminologies of hypothesis testing. So null hypothesis is a claim that needs to be validated through observation. For example, I can make a claim here, which is cats have 4 legs, and this can be a null hypothesis, and we use h sub 0 to represent a null hypothesis, and is actually pronounced as h null. So we try to either reject the hypothesis or do not reject the hypothesis based on observations. So in this case, in order to validate this claim, our observation would need to consist of observation of some cats and see whether they all have 4 legs. The second terminology is an alternative hypothesis, which is a claim which is the conclusion that we will reach if we reject the null hypothesis. Again, using this example, the null hypothesis is cats have 4 legs. So if we reject that claim, then the conclusion we will reach is not all cats have 4 legs. And the alternative hypothesis is denoted as h sub 1. And notice that by rejecting the claim that cats have 4 legs does not mean no cats have 4 legs. Neither did it mean cats had 3 legs. By rejecting cats has 4 legs, the only conclusion we can reach is not all cats have 4 legs. Let's further assume that the only cat that we have access to is the one cat in the neighborhood called Milo. So our decision rule is if Milo has the number of legs that is not equal to 4, meaning Milo has 5 legs or 3 legs, then we will reject the null hypothesis, which is the claim that cats have 4 legs. And if Milo has number of legs equal to 4, then we do not reject the null hypothesis. Now let's look at what the risks are associated with this decision rule. And remember, we are trying to infer the actual situation by making observation on Milo. So the actual situation will be either h null is true, meaning all cats have 4 legs, or h null is false, meaning not all cats have 4 legs. So if Milo happens to have 4 legs, our decision is not to reject h null, And in actuality, if H null turns out to be true, then we are making a correct decision. However, in actuality, if H null is false, then Milo having 4 legs leads us to make an error. It's called type 2 errors in this situation. And on the other side of the equation, if Milo happens to have 3 legs, based on our decision rule, we will reject the null hypothesis. And again, in actuality, if H null is actually true, then we'll be making a second type of error called type 1 error. But if H null is false, and because Milo has 3 legs, that leads us to reject the null hypothesis, then we will be making a correct decision. So how do we know we make an error? So if Milo have 4 legs, which leads us to decide not to reject null hypothesis, and then if we later see another cat that has 3 legs, then we know we have committed a type 2 errors, meaning we do not reject the claim that cats have 4 legs before we saw another cat that has 3 legs, and then we realize we make an error. By this terminology is called a type 2 error. And then if Milo has 3 legs, that leads us to reject the null hypothesis. And that is equivalent to conclude H1, which is not all cats have 4 legs. But again, later on we found out that Milo was actually born with 4 legs and lost 1 in one accident. Then we now know we have committed another error, which is termed type 1 errors in hypothesis testing. Now, how do we know we are correct? The disappointing answer is we will never be sure that we are correct, because additional data could prove us wrong. And that is why the decision on the null hypothesis we can make is either reject or do not reject. We never say accept or prove null hypothesis, because of the very reason that additional information could prove us wrong. And that is the reason that in science one can never prove a theory. A good theory is the one that has not yet been proven wrong. But a new piece of contradictory evidence could prove a good theory wrong. Let's now see how to apply the concepts of hypothesis testing we just learned using the cat example on the weights of cereal boxes. And here are the null hypothesis and the alternative hypothesis. They are appropriate for the cereal boxes example. So the null hypothesis states mu, which is the weight, the average weight of the cereal box, is 368 grams. Therefore, the alternative hypothesis is mu is not equal to 368 grams. But unlike the number of legs of a cat, which is a discrete value, the weight of a cereal box is actually a continuous variable. So in theory, it could take any value on a large interval. So how do we make decision to either reject or do not reject the null hypothesis based on, say, just measuring one box of cereal? Here, if the null hypothesis is true, meaning mu is indeed equal to 368, it's more likely to observe a box of cereal weighed at 370 grams, i.e., a small interval around 370 grams, than to observe a box of cereal weighed at 398, i.e., a small interval around 398 grams. So that gives us an idea of that we should set up a critical values, critical values, so that observing weight that is more extreme than the critical values is a really small probability, such as 5%. And we call these small probability that we need to set as level of significance, and they are denoted as alpha. And based on the critical values we set, we can now define the two regions. One is called do not reject region. The other one is called reject regions. Right? We will use this graph to show what these all mean as to how to make a decision. Here, if the null hypothesis is true, namely mu equal to 368, then the most extreme values coming from observation are those values that fall into the two tails of the distribution. So the 5% most extreme values are those values that fall into these two shaded areas. Each accounts for 2.5% of the total probability. And with the knowledge of the z-scale, the standard normal distribution, we can calculate the two corresponding z-value. One of them will be 1.96. The other one of them will be negative 1.96. And with the reverse transformation, we can calculate the x values based on its raw values measured in grams. And correspondingly, z value equal to 1.96 is associated with the x value equal to 397.4 grams. Similarly, 338.6 grams is the value associated with z equal to negative 1.96. So based on these two values, namely the critical values, we can divide the raw x scale into three regions. The central regions is called do not reject region. The two other regions are reject regions. And the way we will be making decision is as follows. If we measure a box of cereal and the weight from our measurement fall into this interval, then we will conclude we do not reject the null hypothesis. And if the box we measure, the weight of which falls into these two reject regions, then we will reject the null hypothesis. Let's now look at two examples. Say we randomly pick a box of cereal and the measurement turned out to be 370. So based on our decision rule, 370 is between these two values. Therefore, it falls into the do not reject region. Therefore, we do not reject the null hypothesis. In other words, we believe the process is still within control. Let's look at another example. If that one random box of cereal turns out to weigh 398 grams, based on our decision, is the value is out of the do not reject region, is actually in this reject region. We therefore need to reject the null hypothesis. So we conclude the mean is no longer 368 grams, and as a result we need to shut down the production line. Another important concept in hypothesis testing is p-value. P-value is defined for an observation under null hypothesis. Specifically, p-value is defined as, given the null hypothesis is true, it is defined as the probability of observing values that are at least as extreme as this particular observation. Let's again use an example. If we observe a value of 398, namely, we measure a box of cereal and it turned out to be 398 grams. The value they are more extreme than 398 given the null hypothesis is true are on the right side, this shaded area, because these values are more extreme than 398 grams. By the way, 398 is associated with z equal to 2 in a standard normal distribution. But on the left side, this area is also as extreme as 398, meaning if you observe a box of cereal that weighed less than 338 grams, it is as extreme as you observe a box of cereal that weighed more than 398 grams. So the definition of p-value for observing 398 is the sum of the two shaded area on the two extreme tails. Let's now look at the risks associated with following the decision rules we just described. And similar to the earlier example with cats, we will still have this 2x2 4 outcomes. 2 of them are correct decisions, and 2 of them are 2 ways of making errors. What is new here, though, is we can actually associate a probability to each of these 4 outcomes. Let's look at how can we estimate the probability of making a type 1 error. Remember earlier we defined the do not reject regions and reject regions by first setting the level of significance, which is represented by alpha. based on alpha, we define what we consider as extreme outcomes. Those observations that fall into the two extreme tails, and the area of which combined is 5% in our earlier case. So given mu is indeed equal to 368 grams, we can still make observations that would fall into the reject regions. The probability of making such observation is alpha, which is 5%. So those 5% of observations will mislead us to reject null hypothesis, which is committing type 1 error. Therefore, the chance of making type 1 error is simply alpha, the level of significance we set. We now look at how can we estimate the probability associated with making a type 2 error. So the type 2 error occurs when we do not reject the null hypothesis, but in actuality the null hypothesis is actually false. But in order to estimate the probability, we need to further assume we have the knowledge of the true mean. Let's look at this graph. Let's say the true mean is no longer 368. It's already off by 1 standard deviation. So the true means measured in the x scale is now 383 grams. So under these assumptions, the chance of making observations, namely measuring a box of cereal while having the weight falling between the do not reject region, is the probability represented by this orange area. And this area represents the probability that we will commit a type 2 errors, because again, given the mean is off by 1 standard deviation, the chance of making observation that are within the do not reject region is this orange area. And all those observations will mislead us to not reject null hypothesis, while the null hypothesis is false. And to be more specifically, the mu is no longer 368, it's actually 383. So now we need to familiarize ourselves with a few new terminology. So we call this orange area, which is the probability of making type 2 error, beta. So the chance of making the first correct decision is 1 minus alpha, and we call it confidence because it tells us how confident we are to do not reject null hypothesis when it's actually true. And the second way of making correct decision here, the probability associated with it is 1 minus beta, and we call it power because it's the power of the test that could correctly reject the null hypothesis when indeed the null hypothesis is false. A good test, a good hypothesis test, or a powerful hypothesis test is the one with a great value of 1 minus beta, meaning a test that is associated with really small beta. In this case, the beta is actually fairly large. Therefore, 1 minus beta, the power, is fairly small. You can probably reason why that is the case, because the beta, this graph, was constructed for only measuring one box of cereal. So intuitively, we know that if we can measure more boxes, the power should increase. Similarly, our earlier example, if we can make observation on 1,000 cats, the conclusion based on those observations will be a more powerful test result. And one way to reduce the beta will be if we can separate the two means. If we can separate the two distribution more, as a result, the overlapping area is smaller. That is one way to reduce beta and in turn increase the power. However, we do not have control of the actual mean because that's a quantity we do not know. A second way to achieve a smaller beta, therefore a larger power, is to reduce the variance of the distribution. Meaning, if we can make the distribution narrower, then the overlapping area of the two distribution will be smaller, and by which we could achieve a higher power. And this could be done by a sample of observations instead of just making one observation. So instead of using an individual box based on which to make decision on the hypothesis test, we will get a sample of multiple boxes, and we will use its average, which is called the mean of the sample, and we'll use the sample mean to make decision. And we're doing this by taking advantage of this statistical law, which is if x, the variable, follows a normal distribution with the mean equal to mu and then standard deviation equal to sigma, then the sample mean coming from x of a sample of the size of n, namely each sample we make n independent observations, and we denote the sample mean as x bar. This is pronounced as x bar. If we calculate x bar, then x bar is itself a new random variable that also follow normal distribution with the mean equal to mu, but with a much smaller standard deviation. And to be exact, the standard deviation will be sigma divided by square root of n. N, again, is the size of the sample. Let's look at the cereal box for an example. So the raw variable, which is the weight per box, follow a normal distribution of mean equal to 368 and standard deviation of 15. And then if instead of measuring individual box, we pick 25 boxes randomly and we calculate its average, we would arrive at the random variable x bar, and it will follow, because of this law, a normal distribution with the same mu, which is 368, but with a much smaller standard deviation, which is 15 divided by square root of 25, which is 5, and that gives 3 as the standard deviation. Let's now look at what is going to happen if, instead of using one individual box weight, we are using the sample mean of a sample of 25 boxes to conduct the hypothesis test. We will follow the exact same procedure we have described before. So firstly, we set the level of significance as alpha, by which we determine the do not reject regions and the reject regions. But in this case, this distribution is no longer the distribution of x, it's the distribution of x bar. Again, x bar is the sample mean, which is a new variable, new random variable with the same mean but a much smaller standard deviation. And similarly, we assume that the null hypothesis is false. The true mean is actually, again, drifted to 383. But thanks to the reduction of standard deviation, now we can show beta in this case, again, will be represented by the orange area, has reduced significantly compared to our earlier example of using just one box for the test. And so this shows, by using the sample mean for conducting hypothesis testing, we greatly reduce beta. In turn, we greatly increase 1 minus beta, which is the power of the test. So by using sample mean for conducting the hypothesis test, the resulted test is a much more powerful test, meaning we have much more power to reject the null hypothesis when it's false. And going back to the quality control situation, that means we have much more power to accurately monitor the drifting of the production process and to shut it down in a more timely fashion.